Our title today is Atomic Fundamentals. Here is a projection of the periodic table that I gave you in class today. And on this periodic table are listed the 92 naturally occurring elements on this planet and the rest, which are human-made. They exist in labs, some for just very small portions of seconds. Okay, so what distinguishes one element from another? What do all these elements have in common? That's what we're going to talk about today. Okay, so again, you guys, you need to write down every single thing that is written here, plus anything extra that you feel you will need. Okay, so hopefully most of this is going to be a review for you. All matter is made of atoms. Matter, of course, is anything that has mass and volume. There are a limited number of types of atoms that naturally occur. And we call these the elements. So the basic composition of an atom is that at the center of an atom, we call that the nucleus. It's made up of protons and neutrons. And surrounding the nucleus are layers of orbiting electrons. Okay, one thing to keep in mind is that electrons can be removed. Valence electrons, that means the outermost shell of electrons, they can be removed from the atom. Protons and neutrons, no. They are never added or removed unless we're talking about some sort of nuclear reaction. But electrons can. I'm just learning how to use the revealer. Okay, now, what holds an atom together? What holds the electrons orbiting around the nucleus? Well, the attraction of the electrons to the nucleus is the basis of the structure of the atom. So as we'll see in a moment, electrons, and you already know this, I'm sure, electrons have a negative charge, protons have a positive charge, and it is that electrostatic attraction, that electrostatic interaction. And we sometimes call that well, we don't sometimes. It is known as a Coulombic interaction. And we will talk lots more about Coulomb's law later, but basically it is that positive and negative attract one another. And so that's really what keeps atoms together. Electrons attracted to the positively charged nucleus. Okay, so let's talk about these subatomic particles real quickly. So subatomic particles, and when I say that, I'm talking about protons, neutrons, and electrons. Of course, we can go smaller, but we're not studying quantum physics in this class. We're studying chemistry. So we don't need to go any further down to talk about chemistry. Their mass relative to one another, and then their charge relative to one another. So we start with the proton. It's in the nucleus. Protons have a relative mass to the other two subatomic particles as being 1 AMU, atomic mass unit. And its charge is +1. Neutrons, they also have a mass of 1 AMU, but they are neutral. They are not charged. And then last but not least, we have the mighty electron. The mighty electron has only 1/1840th the mass of a proton or neutron. But look at the magnitude of charge. It is opposite, but it is equal to the magnitude of charge of a proton. So even though its mass is so small, its quantity of charge is the same. All right, now, a couple of things I'm going to throw out here, and that is protons and neutrons are held together in the nucleus via the strong nuclear force. As you can imagine, protons are all positively charged, and keeping those protons in close proximity to one another is going to take a pretty hefty force, because positives and positives repel. So neutrons get in between those protons, but overall what holds that nucleus together, proton to proton with neutrons in there, is the strong nuclear force. We also have something called the weak nuclear force. The weak nuclear force is what holds a neutron together. Neutrons are actually a proton and an electron. That's what a neutron is. And it is the weak nuclear force that holds a proton and an electron together to be a neutron. Oftentimes in radioactive decay, we have neutrons spontaneously decomposing into protons and higher energy electrons. Okay, and last but not least, we've got one more force, electrostatic force, Coulombic interactions, that hold the electron in orbit around the nucleus. So that is in terms of negatives being attracted to positives, Coulombic interactions. Okay, so every element, so if we're talking about atoms of gold, right, gold is an element, or oxygen. Oxygen is an element. So each element is made up of atoms that have a common structure. So really now what we're going to talk about is what makes gold different from oxygen, what makes copper different from nitrogen. Okay, it's all about the way that their atoms are composed. So we know that all atoms have protons, neutrons, and electrons. So the atoms of all the elements have a common structure in that they've got a nucleus made of protons and neutrons, and they have electrons orbiting around that nucleus. But what makes one element different from another? Well, because the atoms are slightly different. So atomic number is the number of protons in an atom of an element. And this is really the fingerprint of the atom, is the number of protons. Their numbers of neutrons can vary. Their numbers of electrons can actually vary too, and we'll talk about that in a few days. But however many protons they have, that is really what identifies them as an atom of a particular element. So let's look at the periodic table real quickly and see what I mean. All right, so atomic number. I'm gonna zoom this in, but you should have your periodic table out. Okay, so for instance, here is boron. boron has atomic number of 5. Here is silver. Silver has atomic number of 47. So again, what does the atomic number tell us? The atomic number tells us how many protons are in an atom of that element. And that never changes. If an atom has 47 protons, that means it's an atom of silver. If an atom has 89 protons, that means it is an atom of actinium. Okay, so the atomic number tells us the number of protons, and that is what identifies. That's what gives that atom its identity as an element. So let's zoom in a little bit here. What shall we zoom in on? Let's zoom in on gold, because I like gold. Okay, so here's gold. Au, gold has an atomic number of 79, and that means that all atoms of gold have 79 protons. Gold. Au, oh, I want it to be green. There, I want you to be able to see it. Okay, so its atomic number was, what did I say? I don't remember. Its atomic number is 79. So, atomic number 79. That means that gold has 79 protons. And in a neutral gold atom, we're not talking about a gold ion, but a neutral gold atom has 79 electrons in a neutral atom. Okay, so now the question is, what about the number of neutrons? Now, for elements, their number of protons are always the same, but their number of neutrons can actually vary depending on what isotope of that element we're looking at. So, I'm sure there's a better way of doing this. I'll figure it out. Okay, so the number of neutrons is a little more complicated to figure out. So the number of neutrons is found by subtracting the atomic number from the mass number. So, for gold, it's got 70, it has 79 protons. Okay, so that's its atomic number, 79, right? That's its atomic number. So what we need to do is we need to figure out its mass number. How do we do that? How do we figure out a mass number? Okay, so on the periodic table, this number right here, 196.97, that's its atomic mass. Its mass number is its atomic mass rounded to the nearest whole number. So 196.97, what will that round to? That will round to 197. Let's see if I can remember that while I'm switching. Okay, so 197 is its mass number. Okay, so that is the atomic mass rounded. So, in order to find the number of neutrons in a typical gold atom, we're going to take 197 minus 79, and that is going to give us 8 118 neutrons in a typical gold atom. But not all gold atoms have 118 neutrons. They will vary. They will vary. So what that is we think of this as, or we name this as, isotopes of a particular element. Atoms with equal numbers of protons but differing numbers of neutrons are known as isotopes of an element. And of course, we will, we'll be doing problems about this tomorrow, so we'll get this all cleared up. So what is an example of isotopes? Okay, I like to use the example of carbon. All right. So carbon has 3 isotopes. That means that the element carbon, its atoms come in 3 different varieties. So we've got carbon, we've got carbon 12, we have carbon 13, and we have carbon 14. Okay, these are all isotopes of carbon. Okay, what do you think that 6 is? The 6 is the atomic number that we can find on the periodic table. And what does that describe for us about carbon? This tells us how many protons are in a carbon atom. And in a neutral carbon atom, how many electrons are there. So in each of these 3 isotopes of carbon, there are 6 protons. Because if there's 6 protons, that means it's carbon. Okay, so the numbers of protons never change in an isotope of a particular element. But this, 12, 13, 14, what is that? That is the differing mass numbers. Okay, so carbon 12, if we subtract 6 from 12, that leaves us 6. So carbon 12 has 6 neutrons. Carbon 13, 13 minus 6, carbon 13 has 7 neutrons and 6 protons and 6 electrons. And carbon 14, 14 minus 6 is 8. Carbon 14 has 8 neutrons. Honestly, too many neutrons to stay stable in that nucleus, and so carbon 14 is radioactive, and it will spontaneously decompose. But we'll talk more about that later. All right, so we can find these 3 different kinds of carbon atoms, these 3 different isotopes of carbon on the planet. And they exist in varying amounts. Carbon 12, carbon 13, carbon 14. But they're all here. All right, so the last thing we want to talk about here is why is the atomic mass on the periodic table a decimal number? So carbon has an atomic mass of 12.01. So if we were going to convert that into a mass number, it would just be 12. Okay, but it's not just 12. It's 12.01. So why is that? Why aren't these whole numbers? Well, that's because all elements have various numbers of isotopes, some more than others. And so what does this number, this atomic mass, what does that represent about carbon? It is a weighted average of the masses of all the isotopes of that element. All right, we'll talk about a weighted average tomorrow. You can look it up if you don't know what a weighted average means, but we'll talk about it tomorrow a little bit. And then the last thing I want to leave you with is this. Where do all these things come from? These fundamental building blocks of matter in our solar system. All these elements. Where'd they come from? Where'd they get made? They just appear? Okay, I want you to think about that too, and we'll talk about that tomorrow. All right, we're done.